Hello, my dear friends. How are you doing today? Welcome back to the channel. This is the fourth part of local oscillator leakage concept. In the previous video, I was talking about how we can overcome the effects of a local oscillator in case of downlink signal in 4G OFDM systems. So in this video, I will talk about the concept or strategy applied in case of uplink signal to overcome the local oscillator leakage effects. All right. So first, I will start with the glimpse of what we had discussed in the previous video, especially in the downlink part. So in case of OFDM system, I was mentioning that there are two new blocks which are introduced and which are important for us to discuss this concept. That is, one is subcarrier mapping and another one is IFFT, right? So to overcome the effects of LO leakage in subcarrier mapping for our baseband signal in the frequency domain, I was mentioning that the DC should be made 0. All right. So here note that I have not considered the CP addition or CP removal block for the sake of simplicity. That is one part. And if you see in my previous videos, I had considered only the high channel, but I had not considered the Q channel. Again, this is for the sake of simplicity to understand the concept in a simpler way. I had considered only I channel. Even you can see that I had considered the BPSK where my imaginary term is 0. So the Q channel, I am taking it as 0. But whatever the concepts we had applied for the high channel with respect to cos omega ct, the same thing we can apply even to the Q channel. Only thing is we need to use sin omega ct. So all our equations will hold good for even Q channel as well. So after the output of FFT at the receiver part, okay. So we saw that there is an unwanted DC present, but as we can see that there is no DC signal or DC information, or there is no information sent on the DC. So there is no problem with this. For further processing, we can just eliminate the DC and take all other subcarriers for the processing. So this concept was very simple, and it did not introduce any extra signal processing block. But why can't we use the similar concept in uplink? Why did we need a separate video for uplink? The thing is, in uplink, the concept used is slightly different, which is known as half subcarrier shift. Okay, so uplink is the uplink signal is transmitted from the UV to the base station, and it uses the concept what is known as SCFDMA or DFDS OFDM to generate the uplink signal. So one of the key requirement for this scheme is that the subcarrier allocations should be continuous. So why it should be continuous and all I will not go through here, but right now please note down this. Okay, so considering that, what I would say is, in case of uplink, okay, in case of uplink, uh, the DC is transmitted. In the DC, the information is transmitted. We are not going to skip it, but to overcome the effect of LO leakage, we are going to introduce a new block. Okay, so that new block is called as a half subcarrier shift. This half subcarrier shift uh, we can do by using the properties of Fourier transform, right? So if we want to shift the spectrum by half subcarrier, then we can do this particular operation. So e to the power of j 2 pi by n half corresponds to half subcarrier into n. So after performing this operation, please give it back to the DAC, and let's say we got xp of t, and let's say the the example spectrum would look like this. So to this half subcarrier shifted time domain spectrum, if you take the Fourier transform and if you plot it, then you will see that the subcarriers are all shifted. Okay, so in the subcarrier mapping, we are going to allocate the information, right? Our information would present at these points, even at the DC. Now, if you see here, since the subcarriers are shifted by half, our information is present at this point. So at the DC, there is no information present. So another thing is, at the edge, the null subcarriers are transmitted similar to the top downlink. So right now I'd consider a total number of subcarriers is equal to 4 where our data is sent. So considering the null subcarrier, my endpoint IFFT could be 8 or 16. So when the signal is transmitted and at the receiver, so now the receiver is actually the base station, right? So if you see, if I take if I take this particular direct block, okay, without performing any operation, and if I see the output of xp of t, then I would see that my spectrum would look like this, where the residual dc is present at f is equal to 0. But since the subcarriers are shifted, you will see that the information present at these subcarriers are not corrupted. Maybe some residual of dc might be present over here. So for that reason, we have to remove the effects of DC. We have we need to employ two blocks. One is first DC removal. Another one is off subcarrier shift. We need to shift back, right? Uh, Whatever the shift we had done in the transmitter part. So let's say for now I will keep this DC removal block. Um, I will not perform anything. I will bypass this. Then if I do just off subcarrier shift, okay, shifting back with this particular equation, um, then then if I pass it to FFT and see the spectrum, then I would see that my DC has been shifted to -1/2. So at f is equal to 0, we have the information. So whatever the baseband information which we had transmitted, the information is available. So you take the samples at these points and you do the further processing. But as I was mentioning, there could be some residual of DC present, so it is better even if you remove the DC. So if you are removing DC, remember that before shifting the spectrum, first we should be doing DC removal, and then we should be doing off subcarrier shift. So in that case, what we will see that even this DC component will also be gone. Okay. So I hope the things are clear. In the upcoming video, let us see, what equations to be written to perform this DC removal. Okay, all right. Thank you very much. Have a great day. Bye bye.